can leverage standardized product in order to enable a broad range of prototyping activities in power electronics. My name is Nicolas Chary. I'm the product director at Imperix, and as I suppose that probably not all of you know already who we are a young group of engineers of about 30 people. We are a company located in Switzerland, founded about 10 years ago, and as I mentioned, which is specialized in prototyping activities and research and development activities in power electronics. So overall, we are serving now customers pretty much all around the world, mostly in, as I mentioned, in research and development activities, both in academic and industrial environments. If I have to say in just a few words, what is it that we do? So I would have to group it into three types of products. The first of which, and probably the most important of which, is on the left side, which is the control-oriented products. So this is both at the hardware and at the software level, control systems that people can easily program thanks to typically MATLAB Simulink, and on which they can implement potentially complex control algorithms to be tested together with power converters. The second part of our product portfolios is about modular solutions to build up power converter prototypes. So that ranges from power modules, but also encompasses rack mounting equipments and accessories in order to build up laboratory scale systems for testing. And the third side of our activities, I'm mentioning here sensors, but a bit more general than that. It also encompasses external inductors, filters, transformers, electrotechnical equipment, mechanical equipment around, actually everything that we need all together to give birth to systems working in a laboratory environment. Very practically, a good example and probably the most important part of our activities is related to modular prototyping systems. So this is a story that typically starts with customers sharing with us a schematic of the power converter that they would like to implement. It could be a topology, it could be a microgrid, it could be any kind of distributed energy system. And then we work generally together in order to see how, using our products, we can implement their system. So as you see here, it can be quite a broad range of applications. It can be integrated with different level of readiness or different mechanical aspects. But it quite often turns into systems that are integrated in 19-inch cabinets. In the previous case, this is really something which is based on started on a custom basis. What we also do is provide a range of standardized industrial test benches. So typically the picture here is showing the motor test bench, which integrates a permanent magnet synchronous machine and an induction machine together. And the typical purpose of that is in the internal teaching in the industrial environment. If it's academic environment, it's also related to research and working on control validations, working on algorithms and seeing how they perform in a real life, real power laboratory environment. As a third step, people also using our standard test benches for equipment testing, being with energy storage, with motors, with other aspects. Altogether, I would say that this really benefits in order to accelerate R&D activities, de-risk projects, and really bring ideas faster to market if it's an industrial product, or to a publication if it's an academic environment. Since we have these products available on the industrial side, I would say the benefits that we really bring to our customers are related to working in a unified environment from the start. So things really start together with Simulink when they can really early evaluate the expected performance of their algorithms, then smoothly transition through prototyping phase, building laboratory scale systems, potentially building pre-series products. Throughout all these steps, working directly from Simulink with a unified software environment, always the same, no big breaks in between these steps. This is really what accelerates and facilitates their prototyping activities. This is being supported at the hardware level by the fact that we have two fully compatible identical controllers. We have the B-Box RCP on one hand, which is the very flexible, configurable hardware, which is quick and easy to integrate into different applications. And we have absolutely identical performance with the B-Board Pro, which is the device which is cheap and small enough to be integrated into products. So having this seamless transition in between the two is also an extra help in order to facilitate any transition from the lab to the product or to the field, actually. So we have these two controllers, which we can also use into more advanced control configurations. So here in this example, we have a complete distributed control system, which is using optical fibers for the communication in between the different units. So I'm taking here this example of a complex power converter. It's a cascaded H-bridge with integrated split storage. So in that scenario, the customer wanted us to help them with the prototyping phase, so we integrated the whole system for them. And then they are responsible for the control using our hardware and power hardware and control hardware at the same time. So in that scenario, there is really a controller which is being integrated into each submodule. So there is control at the submodule level, control at the ARM level, control at the system level, which can all be easily implemented and integrated directly from Simulink. Having such performant control solutions is also helping us address industrial applications. So in this example here, we are integrating our B-board controllers into a customized control hardware. So these are the black units that you see on that picture. These hardware controllers being used for replacing old controllers of the tokamak power supply at the EPFL Swiss Plasma Center. And so we end up having our equipment here controlling the 1912 pulse rectifiers that are powering the magnets that maintain the plasma in the correct position and shape. So this is also another example where we have here in that case 19 controllers, all coordinated, synchronized, and implementing a distributed control for all the currents, mostly in that scenario, throughout a customized software interface as well. So to dive a bit into more details regarding how we can have such a broad portfolio of applications, I think it comes on the power side from the fact that we have standardized elements, standardized building blocks, which are our power modules. So on the power side, we have three different types of power modules. We have an half bridge, an NPC, and a full bridge module, which all integrate onboard protections, onboard sensors, and onboard gate drivers. So they are not particularly smart units, but they have sufficient intelligence to at least embed protection and to be easy and quick to integrate together with our controllers. So having these building blocks, we can easily build pretty much any sort of power converter topology with relatively high performance already, meaning it covers a broad range of control validation applications. On the control stage, as I already mentioned, we do have a good communication capability between the units. So the main application of that is simply scalability. So units can be stacked, typically up to 64 units. So that already brings thousands of PWM outputs, thousands of analog inputs all together, which people can integrate as a fully centralized controller. So it means it's one single very big controller, but there are also options to implement distributed control techniques so that they can have master slaves, master configurations, different sorts of control distribution and hierarchization schemes that are quite often attractive for complex power electronic systems. So scalability is one thing, but we are not neglecting performance either, in the sense that already with the CPU, control loops can run up to 200 kilohertz typically already in the CPU. We have a very good timing accuracy throughout the network, meaning that people don't need to care about synchronization between the different units. Every PWM output is really equivalent as being on one single unit. And for applications that also require that, it's possible to use the FPGA for more advanced control technique implementations. So that's overall scalability on both the power and the control stage. How this is being integrated is also flexible, so we can also offer some modularity and flexibility on that. So the basic option is that range of solutions that we call here open and flexible. So that means simply sliding modules in and out of a rack, having potentially some shelves where we have inductors, EMC filters, LC filters, some different configurations. So here again, there are standard options which can be customized upon request, and potentially even some relatively conventional electrotechnical equipment. Here it's a circuit breaker, pre-charge circuit, typically integrating a power converter which is connected to a grid. So that range of solution, open and flexible, is one option, but products can also be integrated here in a different variant that have fully enclosed boxes, which then offer banana connectors, quite typical in a laboratory environment, which offers somehow a bit of a safer and more elegant and better integrated variant for our equipment. A bit as an opposition to this modularity, but nonetheless also to show you how we do things internally. We have recently launched a new product, which is a fully integrated three-phase inverter. So it's kind of the third option, which means we are losing that flexibility that we were showing from the previous range, but we have something which internally nonetheless reuses the same modules as building block, the same controller, the same sort of filtering equipment that we have on the other product ranges, but here all integrated together so that that product can be simply one cable that goes to the wall plug, and which means extremely easy and quick to integrate into a laboratory environment. So there, people then end up with a fully integrated inverter, which offers the same characteristics as the rest of our equipment, but in just one single unique integrated monolithic box. How it works? How it works overall is quite simple. At least this is what we are being told. In general, I would say it works a bit as follows. So people quite often start from our website, from our knowledge base, where we are publishing control implementation examples. So that's documenting how typical standard control implementations are made for different power converter systems. Those examples also feature the source files, so that's Simulink or the Plex files that control those converters. So it's easy to copy paste blocks and actually build your own control based on those examples. The second step, potentially the first important step of the whole implementation process, is running computer-based offline simulations. They can already be used for tuning PI controllers, for instance, so really making sure everything works, that the control algorithms are solid. All these kind of things can be tested in simulation. Then number three, control code, runtime code can be automatically generated thanks to Simulink Coder or Plex Coder, so that people don't need to know anything about programming themselves. That code is being automatically generated, compiled, and then uploaded onto the target. So that's really a quick and one single press button process. And once they have something running, then our software cockpit, I will tell you a bit more later about that, our software cockpit really enables them to produce stimuli, transients, etc., to excite the system and see how well it performs. Overall, as a summary, if I have to summarize a bit what are the strengths of our solutions, I would say, as you have seen, the most important thing is probably that it's really fast to use. Starts from a graphical environment. You can pre-validate many things in simulations. Code is being generated automatically. So this is really quick to use, and people can go early in the lab and really challenge their control in a real environment. At the hardware level, it's also easy to implement. So there are plug and play connections between sensors, modules. The sensors are being powered directly from the controller. So there's not much time that people would lose with auxiliary activities, I would say. And then in some cases for cabinets and systems like that, we can offer pre-wiring services so that people can even save time on those kind of boring activities. And finally, but perhaps quite importantly as well, we can guarantee a safe operation thanks to reliable protections in the controllers, in the modules, so that it really allows trial and error. I mean, it's really able to support even students in the lab so that if something doesn't work, the system simply blocks and people don't risk to break anything. So this is really something that helps, again, going early to the lab. Mentioned about guided readings, we have talked about that already. Turning this into more details, what exactly are the products and the software behind that approach? On the control side, you have already seen two of those controllers, the B-Box RCP, our #1 controller, the B-Board Pro, which is the embeddable variant. But in between the two, we also have the B-Box Micro, which is a smaller version of the B-Box with less IOs, without the networking capabilities, but which is meant to be smaller and cheaper, typically used for teaching applications. So that's potentially an alternative for projects that are a bit less ambitious than some others. Knowledge base I have told you about. It's not actually a product, so to speak, but it's nonetheless an important part of our portfolio. So if you'd like to get an opinion on that, just browse our website, imperix.com/doc. You can see how those examples are being built, how the products can be used, and that's probably what gives you the best possible overview about our solutions. In Simulink, exactly how it works is as follows. So there are, of course, models for each and every of our products in both Simulink and Plex, so that people can really anticipate the behavior of the power modules, of the whole power converters, and run accurate offline simulations beforehand with accurate phase shift, with accurate control discretization, with accurate sampling instance. So all these aspects related to digital control are well modeled and apprehended. On the plant side, on the control side, on the control side, then people can really start reusing their existing models. All they need to do is integrate our input or output blocks into their models so that our hardware is being taken into account in the generation of the control code. It's always possible to switch between code generation and simulation easily by just a toggle switch, meaning that people can really easily iterate in between the testing, process, simulations, whatever, in just one single file, so that from what we have heard, people consider it quite simple and easy to use. When more performance or more special implementations are needed, it's also always possible to combine control implementation in the CPU and the FPGA. So typically in that example, we would have some relatively slow algorithms being run on the CPU and some faster special implementation, here sliding mode control, being implemented in the FPGA. That remains, of course, an optional process, but that's always possible for those who would like to do so. It works by simply reusing the available area, which is not being used by our firmware. So the rest of the FPGA is available for people who would like to implement their own algorithms, systems, modulators, whatever. And during the real-time operation, then the most important part is our software named Cockpit, which, long story short, works as a big and complex oscilloscope. So the main feature is are the triggered scopes, which works like any other oscilloscope for capturing relatively large windows featuring every sample of the control. People can also leverage continuous rolling plots, so that means monitoring variables that are varying a bit more slowly, typically a DC voltage, an energy level, a power flow, a temperature. These quantities are best being monitored with the running plot, and some direct access also possible to specific variables. Actually, overall, every variable in the control can be monitored, tuned in real time without any problem. And what we are now adding to Cockpit in the upcoming releases and current versions and betas, we are integrating a GUI builder so that people can build their own graphical interfaces so that they can easily control a power converter, a microgrid, different units. So enabling them to develop this kind of interface by themselves. So this is a new feature of Cockpit. The transient generator is now going graphic, meaning we can not only generate steps, but easily ramps and other types of profiles, so that the excitation that we can put to the system are being a bit more flexible. And since this summer now we have the spectral analysis option, FFT, THD, whatever, so that we can best evaluate the performance of the controls being implemented. So we have a quite broad product portfolio with different products in control, power, mechanical integration, interfaces for motors, interfaces for hardware in the loop simulators, and of course accessory sensors, electrotechnical equipment, etc. So we have that broad portfolio of products so that we can really support a broad range of applications from standard product and solutions. So overall, I think you can see that we are really giving our best to give real power to your control in order to help people build tailored systems using standard products. We have products and solutions for broad needs and ambitions, so from simple systems with just a few modules to a large power converter integrated in a cabinet, always with that objective that we can support a fast transition from simulation to the lab and get high quality experimental results. We do that again with the objective that we can provide people with continuous support and advice. We have now a team of experienced engineers. This is pretty much 2/3 of the company. And of course, apart from us, there's also a growing online knowledge base. There's a growing community of users, which are all factors contributing to assisting people with their experimental activities. If you wish to know more about our products, I really recommend you to have a look at our website, even visit the knowledge base maybe. This is really a good source and probably the most complete source of information about what we do, and you would have actual implementation examples. Feel free to follow us on LinkedIn as well if you'd like to stay tuned about software releases and other updates. And as I'm unfortunately not able to be with you tonight, if you have any comments, questions, remark, feedback, whatever about this presentation, feel free to reach out to me directly. It would be my pleasure to give you my feedback. Thank you all for being here tonight. It was a pleasure for me to be giving this presentation. I hope that you enjoyed it and that you find it interesting. I'm looking forward to your feedback if you have any. Otherwise, I wish you a very nice evening and continuation of the conference. Thank you.